This is section 12.4. So far in chapter 12, we talked about the visual displays of data. We talked about the measures of central tendency. We talked about measures of dispersion. And in this section, we talk about measures of position. Specifically, we have four objectives: to compute and interpret z-scores, to compute and interpret percentiles. We'll be computing and interpreting deciles and quartiles. And last, we construct and interpret box plots. Now, the z-score is a very, very important concept in statistics. And so that is a concept that will be with you throughout, as long as you take anything related to statistics, the z-score will prominently figure into that discussion. So here's the definition of the z-score. Each individual data item in a sample can be assigned a z-score, which is the first measure of position that we consider. And it is defined as follows. If X is a data item in a sample with a mean X bar and a standard deviation S, then the z-score of X measures the number of standard deviations by which X differs from X bar, the sample mean. It is calculated as follows. Z is equal to X, the data value, minus X bar, the mean of the distribution, divided by S, the standard deviation of the distribution. So in other words, the z-score takes into account all the data values, because the mean depends on the data values, and then it takes into consideration the standard deviation. Again, all the data values are included in that, and so that determines the position. And let's look at a few examples here. It's really easy to compute. Example 1, suppose for a given distribution, X bar, the mean is 340, and the standard deviation is 22. Find the z-scores to the nearest 100th, that means 2 decimals, for these items within the distribution. So for A, the z-score is equal to 349. That's the data value, minus the mean, which was 340, or which is 340, all divided by S, the standard deviation, which is 22. So when we compute this fraction, it's equal to 0.41. So that is the z-score for this particular data value in this particular distribution. So that's A. And for B, it is quite similar. So here for B, the z-score is equal to 300 minus 340, again divided by S, the standard deviation of 22. And that is equal, now notice that 300 minus 340 is a negative number. So that is minus 1.82. So in other words, z-scores can be positive and they can be negative. And of course, the z-score could also be 0. And then for part C, it is 382 minus 340 divided by 22, and that's equal to 1.91. So computing a z-score is really pretty straightforward. Z-scores have many, many applications, but to begin with, we're just using an example of comparing positions using Z-scores. So two friends, Cyrus and Aisha, who take different history classes, had midterm exams on the same day. Cyrus's score was 86 and Aisha's was only 78. Based on Z-scores, which student did relatively better given the class data shown below. So here we have the class mean for each of the students, 73 and 69, and the class standard deviations was 8 and 5. So let's compute the corresponding Z-scores corresponding to their exam scores. So Cyrus's Z-score is his score of 86 minus the mean of 73 divided by the standard deviation of 8. And so he has a Z-score of 1.625. 1.625. That means his score is 1.625 standard deviations above the mean for his class. Now when we do Aisha's Z-score, or Aisha's, so her Z-score is 69. No, her was 78. Sorry, 78 minus the class mean of 69 divided by the standard deviation of 5. And that's 1.8. So who did better? Well, relative to the class, you can say that Aisha's Z-score is higher, so she was positioned relatively higher within her class than Cyrus within his class. Her score is 1.8 standard deviations above the mean in her class. His is only 1.625 standard deviation but above the mean in his class. So that lets you compare apples and oranges in a meaningful way. I'm sure you've heard of percentiles before, but here's a formal introduction. If approximately n% of the items in the distribution are less than the number x, so it's less than, remember that, then x is the nth percentile of the distribution, denoted by p sub n. So you may want to reread this here on your own and see if you can wrap your head around it. It is probably easier when you look at an example, and we do that right away now here. So what we have here is a distribution of the number of dinner customers served by a restaurant on 40 consecutive days. And the numbers have already been ranked from least to greatest. So that's usually a bit of a task if you do it manually. And of course, if you have a Excel or something like that, it's pretty easy to do. But anyway, here they are, all 40 from 10 per row. And so for this data set, we're asked to find the 65th percentile and B, the 88th percentile. So what this means is that the 65th percentile is taken as the item below which 65% of the items are ranked. So in other words, we need to find out what is 65% of 40, since there are 40 data items. So 65% of means times 40. And that is equal to 26. So we're looking for the 26th item. And so So here's 10, 20, 1, 2, 3, 4, 5, 6. But remember, it's below that, so this would be our 65th percentile. So P sub 65 is equal to 68 in this case. So always remember it's below that one. So we have to go to the next one. Again, you may want to reread the definition of percentile. So that's the A part. And for the B part, it's quite similar. The 88th percentile would be 88% times 40. And that is equal to 35.2, but we round that up to the nearest integer, so we round it up to 36. So it's a 36 item. So here's 10, 20, 30, 1, 2, 3, 4, 5, 6. So that would be 75. So P sub 88 is equal to 75. Now notice here we didn't go to the next one because we already rounded it up. So that's why P sub 88 would be 75. 1, 2, 3, 4, 5, 36, right? So here are the percentiles. Example 4, asks for finding deciles. I explain in a moment what that is. Find the fourth decile for the dinner customer data of example 3. So here is the customer data, and the fourth decile simply means 40%. So it's the same similar calculation. 40% of 40 data items would be 16. So we take the 17th data item. So this would be 10, 11, 12, 13, 14, 15, 16. So the next one is 64. So that would be the fourth decile, would be 64. So again, it's the same as saying P sub 40. 40th percentile or fourth decile. Deciles are not used all that often, but they are once in a while. But what is used a lot are so-called quartiles. So that tells you we are subdividing the data set into 4 parts. So for any set of data ranked in order from least to greatest, the second quartile, Q2, is the median, in other words, the middle item, when the number of items is odd, or the mean of the 2 middle items when the number of items is even. So in other words, it's the same as the median rather. And then the first quartile, Q1, is the median of all items below Q2. If you cannot imagine that, we'll do this in just a moment, and then you have a pretty good idea what it means. And the third quartile, Q3, is a median of all items above Q2. In example 5, we are asked to find the 3 quartiles of the data from example 3 of the dinner data. So here are our 40 ranked data, and to find Q2 is simply the middle value of all the data. So you have 10, 20, 30. So the middle value would be the median between the mean value between 65 and 66. So 65 plus 66 divided by 2. Even data set 40 would be even, so the middle values are the mean of the 2 middle values, so it'd be 65.5. So that's our Q2, 65.5. Okay, so that's pretty straightforward. Now, our Q1 is the middle value between the first and the median value here. So we have 20 values, and so between the 10th and 11th value would be our Q1. So in other words, that would be 59 plus 60. 59 plus 60. 60 here, plus 60 divided by 2, and would be equal to 59.5. So it's a value that's between these, that's a mean between the 59 and the 60. Similarly, Q3 would be the median value, the mean value, or the median of the upper part of the distribution above Q2. So it would be between 69 and 70. So between 69 and 70, that's our Q3. So 69 plus 70 divided by 2. And that's equal to 69.5. So here's Q2, which is basically the median of the data distribution. Q1 is the median of the lower part of the distribution, below the median. And then Q3 is the median for the upper part of the distribution, above Q2. The last concept we'll be covering in this section is the box plot, also known as a box and whisker plot. It involves a median, the measure of central tendency. It involves a range, one of the measures of dispersion, and the first and the third quartile, in other words, measures of position, all in one simple visual display. So here's the formal definition. For a given set of data, a box plot consists of a rectangular box positioned above a numerical scale extending from Q1 to Q3, with the value of Q2, the median, indicated within the box, and with whiskers, line segments, extending from the left and right from the box to the minimum and maximum data items. So that may sound a little mysterious, but when we do one of those, it'll be pretty straightforward, as you will see. Again, we were referring to the data that we looked at before for a few times here. So here we are constructing a box plot, and construct a box plot for the 40 dinner customer data of example 3. So we looked at that now a few times, so let's do that again. So here are the data we need for the box plot. We need the minimum, and we need the maximum, and we need Q2 or Q1, and we need Q2, and we need Q3. Now the data value had already been ranked, and when we take a quick look at the data, we find that the minimum value is 46. So the minimum is 46. and the maximum is 88 over here, 88. And we just computed Q1, Q2, and Q3. So Q1 was 59.5, 59.5. Q2, the median, was 65.5, 65.5. And Q3 was 69.5. So now with all the numbers that we need to draw our box plot. So here's the graphical representation of the data. So here's our scale line from the minimum of 46 to a maximum of 88. And here's Q1 at 59.5. Here's our median, Q2, 65.5. And here's Q3, our third quartile, at 69.5. So this is a box, and these are the whiskers extending to the maximum of 88 to the right and 46 to the left. So that's what the box and whisker plot looks like. It's fairly easy to construct. So anyway, I hope this makes sense now, and that you can do this yourself also. So these are just all the values that you need. Minimum, maximum, Q1, Q2, and Q3. And that'll allow you to draw a box and whisker plot. This concludes section 12.4.